Hello everyone. Welcome to the live problem solving session for week 9 of the course Computational Commutative Algebra. Let's summarize the topics of week 9. Let's write down the keywords of the topics. So, in the first lecture of week 9, we started with the degree of Hilbert-Samuel polynomial. So basically, I will just write degree of Hilbert-Samuel polynomial. So basically, if we are given a short exact sequence and then we want to look at the uh, degree of Hilbert-Samuel polynomial of each three modules, then what is the relation between them? So that is what we have seen in the first lecture. Then we have proved the Krull's dimension theorem. So Krull's dimension theorem. So which basically states that the three numerical invariant uh, delta of m, s of m, and Krull dimension of m. So all these three are same. So these three invariants are equal. So where m is a finitely generated module over a Noetherian local ring. So after that, we have done the Krull's principal ideal theorem. Krull's principal ideal theorem. And then somewhat a general version of this, which is known as Krull's height theorem. So both are important. Krull's height theorem. And then we have seen dimension of polynomial rings. So basically, if R is Noetherian, then dimension of the polynomial ring Rx is same as dimension of R plus 1. And we also studied about the dimension of affine algebras or dimension of finitely generated K algebras, means Krull dimension. So Krull dimension of affine domains. Or let's write finitely generated K algebras which are domain. So which is basically the transcendental degree of the fraction field of that affine algebra over the base field. So which are domain. And then we defined what do we mean by saturated chains of primes. So saturated chain of prime ideals. And in case of polynomial rings, all the saturated chains has the same length. So and after that, so to prove that we have done a more stronger version of the Noether normalization lemma. So a stronger version of Noether normalization lemma. So at least we have seen the statement, may not be the, we have not seen the proof, but we have seen the statement. So these are the rough topics of this week 9. So now we can solve some problems based on these topics. Okay, so let's do some problems based on height of ideals. So let R be a Noetherian ring and I subset of J be two ideals in R. Then height of I is less equals to height of J. Okay, prove that. So prove that if so let R be a Noetherian ring. So in a Noetherian ring, we know height of every ideal is finite. So let's take I subset of J, two ideals. So then we have to prove height of J is less equal to, sorry, height of I is less equals to height of J. So the problem looks very simple. So let's do it. So let's write down the definition first. So what is height of I? So height of an arbitrary ideal is defined in terms of height of the prime ideals which contains that ideal. So it is basically minimum of height of those prime ideals P such that P belongs to V of I. And V of I is basically set of all those prime ideals of R which contains I. And so let's write down the height of J also. So it is minimum of height of P such that P belongs to V of J. So since I subset of J, so what can be said about V of I and V of J? What is the relation between them? So if P contains J, then definitely P contains I, right? So if P belongs to variety of J, that will imply P belongs to variety of I. So V of J is subset of V of I. So we will have the reverse containment. So this collection is bigger than this collection or this set. So if we take a minimum over a bigger set, then we will get less, right? So this implies uh, minimum of height of P such that P belongs to V of I should be less equals to minimum of height of P such that P belongs to V of J. Because here we are taking minimum over a bigger collection. So we may have more elements which may be less than. And this implies height of I is less equals to height of J. So here the logic is very simple. So one thing I want to put as remark. So this is just an observation. So if P properly contained in Q are prime ideals, then height of P should be strictly less than height of Q, right? Because here we are adding one more prime Q itself, so height will be at least one bigger than the height of P. So we'll use these facts. So okay, now let's do a quick observation also. I will put this as problem number 2. So true or false. So here we are saying if I is subset of J, then height of I is less equals to height of J. So if we take proper containment, then is it a proper less than? So let R be a Noetherian ring and I is proper subset of J be two ideals of R. Then height of I is strictly less than height of J. So it is true or false. That we have to check. So if I and J are prime ideals, then it has to be strictly less. That we have put as a remark. But what about general ideals? So let's see an example. So let R be the polynomial ring in one variable x and I be the ideal generated by x square and J be the ideal generated by x. So then I is a proper subset of J. That is clear. But what about height of I and height of J? So here height of J is the height of the ideal generated by x and ideal generated by x is the maximal ideal here. So height of J is clearly 1 because height of J should be less equals to dimension of the ring, which is 1 here, and we have a chain 0 subset properly subset of x. So this is a chain of prime ideals of length 1. Or we can use the Krull's principal ideal theorem because x is a non-zero non-unit, so its height has to be 1. So similarly, as a similar reason, height of I is also 1 because again we can use the Krull's principal ideal theorem to x square, or we can directly do it by definition also. So because here V of I is just the prime ideal generated by x, we have only one ideal and height of this is 1. So height of I is also 1. So I is properly subset of J, but height of the both ideals is 1. So this statement is false in general. Okay. So let's do some examples. Then it will be more clear. So problem number 3. So let R be the polynomial ring in 4 variables x1, x2, x3, x4. Right? Now determine the height of the following ideals. So the first one is let's say I equals to ideal generated by x1, x2, x3, x4. B, the ideal I is ideal generated by x1, x4, comma x2, x4, comma x3, x4. Okay, here let's take up to x3. And C, we can take I equals to ideal generated by x1, x2 intersection with ideal generated by x3, x4. And let's take D as the ideal generated by x1 comma x2 intersection with, okay, let's take x1 just, and intersection of this with x2 x4 comma x3 x4. Okay, so let's do these 4 examples. Okay, so the first one, so here I is the ideal generated by x1, x2, x3. So it is generated by 3 elements. So this implies height of I is less equals to 3. This is by Krull's height theorem. Because it has a generating set containing 3 elements. Now also note that if you take 0 properly contained in x1, properly contained in x1, x2, properly contained in x1, x2, x3, then this is a chain of prime ideals. So this is a chain of prime ideals of length 3. So this will imply height of I has to be at least 3. But from this one and this one, we can conclude that height of I is 4. Sorry, height of I is exactly equals to 3. So this gives the first one. So its height. So it is. Now let's do the second one. So we will use the Krull's height theorem as well as the definition. So let's see how to do this. So in B, the ideal is ideal generated by x1, x4, x2, x4 and x3, x4. So this we can write it as ideal generated by x4 times ideal generated by x1, x2, x3. And this is same as ideal generated by x4 intersection ideal generated by x1, x2, x3. Because this ideal and this ideal are co-prime, so their intersection and product is same. So that's why we can write this. But these both ideals are prime ideals. In particular, they are primary ideals. So this is a primary decomposition. So the above is a primary decomposition of I. So associated primes of I, which is basically same as associated prime of the module R mod I, is same as ideal generated by x4 and ideal generated by x1, x2, x3. So both are actually minimal primes of R mod I because they are incomparable. So now height of I is basically, by definition, it is minimum of height of P such that P belongs to variety of I. So we need to take minimum, right? So we can vary this over the only minimal primes also. So we can have a smaller collection. So this is same as minimum of height of P such that P belongs to minimal primes of I. So this is a general situation. So this we can apply in any case, but I'm writing it here because I will be using it here, or maybe in the next problems also. So if we use this, so then it is just minimum of height of ideal generated by x4 comma height of ideal generated by x1, x2, x3. And height of x4 by Krull's principal ideal theorem, it is 1, and height of this ideal is 3 that we have done in the first problem. So this is minimum of 1 comma 3 and which is 1. So height of the second ideal we have got, this is 1. Okay, now let's do the third one. So third one is very simple. So this is ideal generated by x1, x2 intersection ideal generated by x3, x4. So this is already given in primary decomposition form. So this will imply associated primes of I is x1, x2 and x3, x4. In fact, this is the minimal primes of I. So height of I is, by definition, it is minimum of, so it is minimum of height of these two ideals. So height of x1 comma x2 and height of x3 comma x4. And again, as in the first problem, so we can use the same method to determine height of these two prime ideals. First by using Krull's height theorem, then by getting a chain of prime ideals. So it is basically 2. Both the heights are 2. So height of I has to be 2 here. So third one is also done. Now the fourth one. So it is ideal generated by x1 and ideal intersection with this one. So let's do this. So here I is ideal generated by x1 intersect with ideal generated by x2 x4 comma x3 times x4. So this we can write it as ideal generated by x1 intersect with ideal generated by x4 times ideal generated by x2 comma x3, this product. Again, this ideal and this ideal is are co-prime, so the intersection will be same as product will be same as intersection. So this is same as ideal generated by x4 intersection ideal generated by x2 x3, and this is clearly a primary decomposition. So this will imply, and all these three ideals are incomparable. So these are the minimal primes. So the minimal primes are ideal generated by x1, ideal generated by x4, and ideal generated by x2, x3. So height of I is minimum of height of x1, height of x4, height of x2, x3. Again, use the Krull's principal ideal theorem and Krull's height theorem. Then it is just minimum of 1, 1, and it is 2. Height of this one is 1, this one is also 1 by Krull's principal ideal theorem. For this, it will be 2 by Krull's height theorem, and we can get a chain of prime ideals of length 2. So this height is basically 1. So the fourth one is also complete. So this is one method to compute the height of ideals. Also, we can compute it in Macaulay too. So you may search in the web what is the command for that. Okay, let's move on. So this is problem number 4. So which of the following, so we need to check that the following statements are true or false. Check that if the following statements are true or false. So the first one is there is no zero dimensional okay, there is a there is a zero-dimensional local ring which is non-Noetherian. The second one is in a Noetherian ring, there is no prime ideal of height 1 which is not principal. And the third one is there exists a minimal prime of a principal ideal of height 0. Okay, principal ideal in a Noetherian ring of height 0. Okay, there are three statements and we have to check they are true or false. So let's start with the first one. So first one says there is a zero-dimensional local ring which is non-Noetherian. So this is some we need to find some, either we have to find some example or we have to disprove this statement. So if we, so a zero-dimensional local ring which is non-Noetherian. So that means it is a local ring R comma M, and for a local ring dimension of R is basically the height of the maximal ideal. So height of M has to be 0 but R has to be non-Noetherian. Means there exists an ideal which is not finitely generated. So let's see this example. So let R be the polynomial ring in infinitely many variables, and take the quotient of this by the ideal x1 comma x2 square comma x3 cube and so on. Then we have already seen R is a non-Noetherian local ring. Non-Noetherian local ring with the maximal ideal is x1 bar comma x2 bar and so on. In fact, this is the only prime idea. In fact, spectrum of R is just M. So, and we have already seen that will imply that dimension of R is 0. And it is non-Noetherian because this maximal ideal itself is not finitely generated, because we need infinitely many elements to generate it. We cannot generate it with finitely many elements. So the first one is true. So this one is true. Now what about the second one? So we need to check that the second one is true or false. So here the second one says that in a Noetherian ring we cannot have a prime ideal of height 1 which is not principal. So it says we cannot have a non-principal prime ideal which is height 1. So let R be the subring of the polynomial ring, this one, and let's take P be the ideal generated by x square and x cube. Then what can be said about dimension of R or height of P here? So here uh, dimension of R is 1. So that is this is we have seen in the earlier live sessions, because R subset of Kx is an integral extension. So since this is an integral extension, so dimension of R is same as dimension of Kx, and which is 1. And height of P should be less equals to the dimension of the ring, which is 1. And R is a domain, right? So also 0 is properly contained in x square comma x cube is a chain of primes. So height of P is exactly equals to 1. But here this P is not a principal ideal. So we have got a Noetherian ring and a non-principal prime ideal which is height 1. So the statement is false. So we have got a counter example. So in a Noetherian ring, we can have non-principal prime ideals which has height 1. So now let's see the third one. So there exists a minimal prime of a principal ideal in a Noetherian ring of height 0. So we need to find a principal ideal in a Noetherian ring which has height 0 and whose so means it has a minimal prime which is also of height 0. So let's see. So let R be the ring kx modulo ideal generated by x square. So this is a Noetherian local ring, and let I equals to ideal generated by x mod x square, the maximal ideal of R. So then uh, height of I is same as dimension of R, because R is a local ring with the maximal ideal I. and dimension of R is basically 0 because dimension of kx is 1 and we are going modulo by a non-zero divisor and non-unit. So because x square is a non-zero divisor, so we are going modulo by a non-zero divisor, so the dimension will be reduced by 1, so its dimension is 0. So also note that I is a prime ideal. In fact, it's a maximal ideal. Uh, so minimal primes of I is same as I. So we have got a minimal prime ideal of height 0. And also it's a principal ideal because it is generated by x. So we can write it as x bar. And I is also principal. So the third statement is true. So we have got one example of this kind. So we have got an example of a principal ideal in a Noetherian ring which has a minimal prime of height 0. So the ideal itself is of height 0. Okay. Now let's do some other applications of the Krull's principal ideal theorem. So this is problem number 5. So let R be a Noetherian ring and let P properly contained in Q be two prime ideals of R. Then show that if there exists a prime ideal P prime such that P is proper subset of P prime and it is proper subset of Q, then there exist infinitely many prime ideals in between P and Q. So what this statement is saying is, so suppose R is a Noetherian ring and you have prime ideals P which is proper subset of Q. Now between P and Q, if you have another prime, if there exists a prime ideal in between P and Q, then there will be infinitely many prime ideals between P and Q. So in between P and Q, there cannot be finitely many prime ideals. If there is a prime ideal, then there will be infinitely many prime ideals. So let's prove this. So let P prime be a prime ideal such that P proper subset of P prime proper subset of Q. So we are assuming in between P and Q there is a prime ideal. Then we have to prove that there exist infinitely many prime ideals between P and Q. So assume, so for we will prove this by contradiction. So we are assuming that there are, so assume there are finitely many prime ideals in between P and Q. Then we have to find some contradiction. So, so if we replace R by R mod P, then we can assume R is an integral domain because R mod P is an integral domain. So replace R by R mod P. So what we are doing is, so here is our ring R and here we have a prime ideal P which is contained in Q, and we will work with only those prime ideals which lies between P and Q. So we are going modulo P and localized at Q. Then we can only focus on prime ideal lies between P and Q. So first we are going modulo P. So if we replace R by R mod P, then we can assume P is 0 and R is an integral domain. So R is a domain. So we are assuming P is 0, then R is automatically an integral domain. Again, by localizing at Q, we may assume R is a local ring or is a local domain with the maximal ideal Q. So what is the situation now? So now R comma Q is a Noetherian local domain such that there are finitely many prime ideals between 0 and Q. So this is the current status after those reductions. Now we need to arrive at some contradiction. So let now for every non-zero non-unit element x belongs to Q, let Px be a minimal prime of the ideal generated by X. Right? Then uh, if we take union of the elements X or the ideal Px such that X belongs to Q, then it has to be equal to Q, because X is varying over every element of Q. So X is itself in Px. So this union has to be Q. But this has to be a finite union. Uh, okay, let me write. Now height of Px is equals to 1. This is by Krull's principal ideals theorem. Principal ideal theorem. And so by the hypothesis, by the assumption, not so, it will be also, there are only finitely many Px, because every Px is an ideal between 0 and Q. So because 0 is proper subset of Px and proper subset of Q. So this is a finite union. So thus we have Q equals to union of, let's say, Px, X belongs to Q, and this is a finite union. So now we can use the prime avoidance lemma. So by the prime avoidance lemma, Q is equal to this, means Q is subset of this union of primes. So Q has to be contained in some Px for some X belongs to Q. But Q is maximal. So that will imply Q is equals to Px, because Q is maximal. But this will imply height of Q is equals to 1, because height of Px is 1. But this is a contradiction, which is a contradiction, because height of Q, because P is proper subset of P prime is proper subset of Q, that will give height of Q is at least 2. So we are getting a contradiction, means we have assumed something wrong. So hence there are infinitely many prime ideals. So there are infinitely many prime ideals between P and Q. So this completes the proof. So this problem is basically an application of Krull's principal ideal theorem and prime avoidance lemma. So if you have a chain of primes, and in between P and Q, if you have one prime ideal, then there must be infinitely many prime ideals. So this is the fact. So let's see a nice consequence of this result. So one easy observation that I put as remark. So from the previous result, we can conclude that there does not exists a Noetherian ring R uh, such that its prime spectrum looks like a chain. P0 is proper subset of P1, proper subset of P2. So there cannot be a Noetherian ring R which has only three prime ideals and it forms a chain, because in between P0 and P2 we have one prime ideal, then there has to be infinitely many prime ideals. So a prime ideals whose spectrum looks like this, it is not possible. Okay, so let's see some more application of this result. So it is problem number 5. So the next is problem number 6. So problem number 6. So let R be a Noetherian ring which has only finitely many prime ideals of height 1. So R is a Noetherian ring and it has only finitely many prime ideals of height 1. Then show that its spectrum is finite. So spec of R is a finite set and dimension of R is exactly equals to 1. So what it says, so here R so here R is a Noetherian ring and it contains only finitely many prime ideals which has height 1. So then we have to prove that its spectrum is a finite set and its dimension is equals to 1. So it has two parts. So let's prove this one by one. So we have to prove that spectrum is a finite set and the second part is dimension is 1. So what we will do is, so the first claim is every prime ideal in R of height 1 is maximal. So we will prove that if we take a prime ideal P of height 1, then it has to be a maximal ideal. So this is our first claim. Okay, so this is claim 1. So let P belongs to spec R such that height of P is 1. So we have to prove that P is maximal. So for contradiction, assume that P is not maximal. So assume that P is not maximal. So then there exists a maximal ideal M which properly contains P. Now since height of P is 1, so there exists a prime ideal in R which is properly contained in P. Thus we have a chain Q proper subset of P and proper subset of M. So it is chain of primes. Since Q and M both are, so all these three are primes, and in between Q and M we have one prime, so then we have infinitely many prime ideals. So thus, okay, so by the previous result, there are infinitely many prime ideals between Q and M. Right? Now, let P prime belong to spec R, which is contained in Q and M. Proper subset of properly contained in M and properly contained Q. Then uh, height of P prime is at least 1 because it properly contained Q. Because Q properly contained in P prime. But if height of P prime is greater than 1, then there will be infinitely many prime ideals between Q and P prime, and they have height 1, which is a contradiction because by the hypothesis there are only finitely many prime ideals of height 1. So height of P prime is 1. So every ideal between Q and M has height 1. Thus, every ideal between Q and M has height 1. But we have infinitely many of them. So that is also contradiction. But they are infinitely many in numbers, which is a contradiction. Because we have only finitely many prime ideals of height 1. So we cannot have any prime ideal between Q and M, but P is one such. So what we have assumed is wrong. So P has to be a maximal. Thus, P is a maximal ideal. So every prime ideal of height 1 is maximal. So dimension is equals to 1. Hence, dimension of R is equals to 1. So one part we have proved. Now we have to prove that the other part, that spectrum of R is a finite set. So we already proved that height 1 prime ideals are finite in number. Now the only prime ideals are height 0 prime ideals. Now for each P belong to spec R, height of P is less equals to 1 and height 1 prime ideals are finite in number. Also, height 0 prime ideal means it is a minimal prime. It is a minimal prime of the ring. So height 0 means it's a minimal prime. Now since R is Noetherian, minimal prime of R, it is also a finite set. So hence we can immediately say spectrum of R is a finite set, because spectrum of R contains only height 1 and height 0 prime ideals. Height 0 prime ideals are minimal ideals which are also finite in number, and height 1 prime ideals are finite in number that is given. So spectrum of R is a finite set. And this completes the proof. So these two are nice applications of this previous result. Okay, so these are some little bit lengthy problems. Now let's do some easier ones. So it was problem number 6. So the next is problem number 7. So it is true or false. So let R subset of S be to Noetherian rings. then the cruel dimension of R is less equals to cruel dimension of S. So it is true or false. So if a Noetherian ring R is contained in another Noetherian ring S, then dimension is also less equals to. So dimension of R is less equal to dimension of S. So this is true or false. So if this extension is integral extension, then this is true. That is what we have already seen. But if it is not an integral extension, then what happens? So let R be the ring of integers Z and S be the field of rational numbers. Then clearly R is contained in S, but what is dimension of Z and dimension of Q? So dimension of Z is 1 because Z is a PID which is not a field, and dimension of Q is 0 because Q is a field. So this statement is false. So if this is an integral extension, then it will be true. But if it is not an integral extension, then it need not be true. So this is actually very easy. Okay, let's move on. So problem number 8. So this is also true or false. So the statement is in a Noetherian ring, the set of all prime ideals satisfies descending chain condition. So we know about ascending chain condition ACC and descending chain condition DCC, right? So ACC means if you have an ascending chain of ideals, then it has to be stabilized at some point. And if this is true for every ascending chain of ideals, then the ring is Noetherian. That is we know. So in a Noetherian ring, every chain of ideals satisfies the ascending chain condition. And the dual one, the descending chain condition, it is true in a Artinian ring. It is true for any descending chain of ideals in a Artinian ring. So in this statement we are saying if we have a Noetherian ring, then if we take descending chain of prime ideals, then it has to be stabilized at some point. And this is true for any chain of prime ideals. Is this true in a Noetherian ring or not? That we have to check. So let R be a Noetherian ring and let P naught properly contained in, okay, uh, P naught contains P1, contains P2 and so on, be a chain, okay, descending chain. descending chain of prime ideals. But uh, we are in a Noetherian ring. Since R is Noetherian, so height of P is finite, right? So if we start with a, if we have a chain of prime ideals which ends at P, so that has to be a finite in length. So the chain star has to be finite in length. Hence, every descending chain of primes must satisfy the DCC condition. So this result is true. So this is true because height of every ideal is finite. In particular, height of P is finite. That is by Krull's height theorem. So this is an application of Krull's height theorem. So one thing I put this as remark. So in a Noetherian ring, this set of all prime ideals satisfies both ACC and DCC, both ascending chain condition and descending chain condition. Now what about the converse? What about the converse? Is it true? So let's put this as a next problem. So so it is also true or false. So let R be a ring such that the set of all prime ideals satisfies both ACC, means ascending chain condition, and DCC. Then R is Noetherian. So is it true or false? So it is basically the converse of the above remark. So we know in a Noetherian ring, the set of all prime ideals satisfies both ACC and DCC. So is the converse is true or not? So we have already seen this important example. So take the polynomial ring in infinitely many variable and go modulo by ideal generated by x1, x2 square, x3q and so on. Then this is a local ring. In fact, this has only one prime ideal. Then R has only one prime ideal. So R satisfy. So the set of all prime ideals in R satisfies both ACC and DCC. But R is not Noetherian. So this statement is false. So the converse is not true. So this particular example gives counter example for so many things. So it is an important example. Okay, so to do the next problem, we need to state one theorem. I think it has not been done in the lectures. So let's do it here because it is important. Uh, so it is known as Krull's intersection theorem. So it is basically an application of the Attendee's lemma and Nakayama's lemma. So let's write down the statement. So let R be a Noetherian ring and M be a finitely generated R module. So M be a finitely generated R module and I subset of the Jacobson radical of R. So I subset of Jacobson radical of R and ideal of R. Okay. Then so we can take the sum module I power n m for any positive integer n, and if we take the intersection, then this intersection has to be 0. So this is the statement of Krull's intersection theorem. So the proof is very easy. It uses Attendee's lemma and Nakayama's lemma both. So you may try to prove this using those two lemmas, or you may refer to standard textbook. So I will not do the proof. I will use it to solve the next problem. So here R is a Noetherian ring, M is finitely generated R module, and I is subset of Jacobson radical of R. So this thing we need to apply the Nakayama's lemma. So in particular, if R comma M is Noetherian local and I is proper ideal, then also it is true because M is the Jacobson radical. Okay, so let's do the next problem. So it is problem number 10. So let R comma M be a Noetherian local ring and P be a principal prime ideal such that height of P is equals to 1. Then so that R is a domain. So what is given? Let's write down one by one. So R comma is Noetherian local, P is principal ideal, let's say it is generated by X, and height of P is exactly equals to 1. So this three information is given and we need to prove R is a domain. So let's prove this. So we want to prove R is a domain. So to prove a ring is domain, it is sufficient to prove that the zero ideal is a prime ideal. Now P is principal, so let P is ideal generated by X. Since P is principal. Okay. Also, since height of P is 1, there exists Q belongs to spec R such that Q is a proper subset of P. Right? Because height of P is 1. Now claim that Q is equals to 0. Because Q is a prime ideal. So if we can show that Q is equals to 0, so 0 will be prime ideal. Then R is an integral domain. So how to prove this? So let Q is non-zero and let 0 let a Y be a non-zero element in Q. Then Y belongs to P, which is ideal generated by X because Q is subset of P. So that will imply Y equals to A times X for some A belongs to R. Now Y belongs to Q. This will imply AX belongs to Q. And this will imply A belongs to Q because Q is prime ideal and X does not belongs to Q. And why X does not belongs to Q? Because Q is proper subset of P, which is ideal generated by X. So if X belongs to Q, then P will be subset of Q. So P will be equals to Q. So again, A belongs to Q, which is subset of P ideal generated by X. So again, let's play the same game. So this will imply A equals to R times X. And this will imply, okay, not R, let's maintain some sequence. So A will be A1 times X. For some A1 belongs to R. And this will imply Y equals to A1 x square, right? And this will imply y belongs to p square, which is ideal generated by x square. So continuing this, we will get y belongs to p power n for all n greater equals to 1. And this will imply y belongs to intersection p power n where n is greater equals to 1. So this will imply y belongs to intersection the maximal power of the maximal ideal n greater equals to 1 because p is subset of n. But this intersection is 0 by Krull's intersection theorem. So this is by Krull's intersection theorem. And this will imply y is equals to 0. But this is a contradiction because we have to assume y is non-zero. So this is a contradiction. Hence, q has to be 0. So 0 is a prime ideal and this completes it. So this is an easy application of Krull's intersection theorem. So in our case, I is equals to the maximal ideal and this M is the ring itself. So I think we have done sufficient problems. So it is better to stop here and we will meet in the next live problem solving session. Okay.